So matter and particles. So here we have a picture of space. Space is just a nice view of what it can look like without much matter in it. And space is sort of a good place to figure out where all of our matter comes from, because matter is basically composed mainly of hydrogen, and space is the main constituent, main container of that. So all matter is composed of tiny particles. We know that, and we call them atoms, but we've known that for a long time intuitively. These particles interact with one another through collisions and vibrations. Vibrations, sort of by extension, are collisions, but collisions, so when two particles collide with one another, that's how they interact. They don't do any sort of non-contact interactions. They don't just, attract one another. When they collide, they tend to interact. And vibrations as well. So when they kind of bump into each other through vibration, that's how they interact with one another, okay? So these particles that we've talked about up here can be either elements, molecules, or compounds. So in the previous lessons, I've talked about what elements, molecules, and compounds are. And so these particles in this particle theory can be composed of any one of these three, or any mix of these three, okay? So in different states, the particles of the substance interact differently. If I'm in a liquid state, my particles will interact differently to if I'm in a solid state, or if I'm in a gas state. Each of these has different ways of interacting, and that sort of is why different states have different properties, simply because their particles interact differently. Okay. So the particle nature of gases. So the first one we're going to look at is gases, because this is sort of where the particle theory sort of came from. So the kinetic theory of gases is used to predict the physical properties of a gas. So the kinetic theory is just, an extension of the particle theory. The model assumes that the particles in a gas are well spaced. So you can see here they've got a fair bit of space between them. And each particle moves in a random direction and at random speed. So you can see that each of these particles is moving in a random direction, and the length of these arrows tells me how fast they're going. Okay, so for physics students, this should be clear. This is vector diagrams. So you can see here, this one's traveling at a sort of biggish speed, and this one's not traveling very fast. And they're all traveling in different directions. This one's traveling at a very fast speed, and this one's sort of a moderate speed, and they're all going in different directions. And that's what this model assumes, that all of the particles are free to move in random directions and free to move at random speeds until they interact with one another. So the only way to change the direction or speed of a particle, so the only way to change this particle from going this way and at this speed, is for a particle to collide with another particle. If, for instance, this particle and this particle collided, then they would bounce off each other and travel at different speeds and in different directions as well. That's the only way we can change their direction or speed, by them colliding with one another. Now this theory can explain gas pressure. So if you put lots of gas particles into a small container, you get what's called pressure, as the pressure relates to the number of collisions between gas particles and the wall of the container. The wall of the container gets hit by the particles because they're traveling at different speeds and in random directions. So they hit the wall and then bounce off. And because they hit the wall, for physics students, there's a momentum change. So a force is imparted on the wall. So that force, or that distribution of force over the area, is what we call pressure. Okay, so here we have animation, which I'll get to in a sec. But the compressibility of gases, so the reason why we can compress a gas, is simply because of the huge space between the particles. So as you can see here, there's lots of space between each of these particles. And so if we were to squash the volume down, they would still be able to exist, but they would just have less space to move around. And so we can compress the gas, essentially. So you can see here, if we watch these particles, they travel in random directions until they hit each other, and then they tend to also hit the wall and bounce off, right? And the number of times they hit the wall is related to the pressure in that system. So the more times they hit the wall, the more pressure. The less times they hit the wall, the less pressure. Okay, so that's how these collisions affect the pressure inside a container. Okay. Why are gases easily compressed? Okay, so to answer that question, we'll open with this diagram. We'll look at the diagram first, and then we'll look at the text. So you can see here in this diagram, we've got what looks like a water molecule maybe. This other possibly oxygen molecule, could be anything, could be any diatomic molecule. Now if you look, there's plenty of free space in the left-hand side when the piston is at the top. Okay, lots of free space for the particles to fill. Now if I push the piston down, you can see that they're still able to survive, so to speak, but they just occupy less space. There's less free space for them to move around. And that is in essence what compression, or why gases can be easily compressed. So compression requires that particles are pushed closer together. So when you compress something, you're pushing the particles together. Now in gases, the particles have a lot of empty space, as I mentioned, lots of empty space here. So they can be pushed together more easily, right? Because there's lots of empty space anyway. So you can see when we push down, the empty space sort of disappears and it's taken up by gas particles. So the more we compress it, the less empty space we have. And that's really the reason why gases can be easily compressed. How does the kinetic theory explain the fact that the pressure of a gas in a sealed container remains constant indefinitely, provided the volume and temperature are kept constant? So what we're saying is, in the kinetic theory of gases, the pressure in a container is the same as long as you keep the temperature and the volume the same. If the volume and temperature are the same, the pressure will remain at that level all the time. Okay, so here we have this animation once again. Remember that the pressure is related to how many times these particles strike the wall. Okay, so they hit the wall, and that will be what we call pressure. If the temperature is the same, then the particles will all be traveling at approximately the same speed, or the average speed of the particles won't change. Because if we increase the temperature, obviously the speed will increase. And so if the speed increases, you've got more likely chance of them hitting the wall, because all of a sudden they can move faster. They'll hit the wall more frequently. But if we keep the temperature the same, then they can only move at a certain speed, which is related to the temperature. They'll just hit the wall at the same rate as what they were doing before. Now additionally, if for instance now we just cut the volume there, you can see that the particles will have less space, so they'll also hit the wall more frequently. So we can't shrink the volume. So if they hit the wall more frequently, then the pressure will go up. So by keeping the volume the same, we should expect that the pressure stays the same as well. So that's why, but we'll look at the answer. So the collisions between the gas molecules and the container are assumed to be elastic. So that means that when they hit the wall, essentially no energy is lost by the molecules. So they'll bounce off the walls, creating the same pressure indefinitely. So basically they'll hit the wall and come off, and no kinetic energy is sort of lost. Okay, so they'll hit the wall and come back, and they'll have the same kinetic energy as when they hit the wall. Since the velocity and directions of the particles are random, then the proportion of time the particles hit the wall will also be the same, as long as the conditions are the same. So you've got to keep the conditions the same, otherwise you can't compare them. Explain why gases spread to occupy the available space. Okay, so why does gases spread out to occupy the available space? So here we have the picture again. They travel in all different directions, and that's key. So in a confined space, so a very small space, particles collide very regularly. So they hit each other really rapidly and constantly change directions of motion. So let's say we have this confined space here. If you watch the particles, they just keep banging into each other because they're so big compared to the space. So they keep banging into each other very rapidly. And they'll keep changing their direction because they keep hitting each other. But once the container is expanded, so let's say we took up the board space now, up to me, the particles traveling away from the majority of the particles will continue to move in a straight line. Let's say this particle here. If we expand the board space, right, now it can go down here, but there's no particles in the way. So it'll just keep going and going and going until it hits the wall. So it'll keep traveling in a straight line until a container confines them to a particular space. Now the continued collisions of the particles will eventually send more particles away from the group, spreading the gas out to fill the room. So this one has already gone away, but these four are going to keep hitting each other. And eventually one of them is going to hit and send the other one maybe out this way. And it's going to keep going until it hits a wall as well. And that's going to keep happening, which will eventually spread out all the particles. So that's why gases always fill up the room, because the collisions in this confined space send the particles outward, and those particles will keep traveling outward until they hit a wall, come back and sort of interact, which will eventually fill up the room with gas.